Ooh, okay. We're getting some good amount of votes. Thanks, everybody. Okay. So, like I said, this is a type of question that we will come back to it again and again, and you will definitely have a question that looks a lot like this on your final exam, maybe multiple questions, where I give you some type of scenario and I ask you specifically, how is that going to map to a graph? And so when we're working with graph theory, the first thing we need to determine is what are our node elements? What are those circles, those vertices? That's the word we're going to use for that. And what are the things that connect those vertices together? What are the relationships? What are the edges is the word we're going to use for that. So let's see. Does anybody want to raise their hand and share with us some of the things they chatted about? What would you choose as your vertices? Anyone want to share? Yeah. Profiles. Yeah, I agree. Let's see if I can click in. Whoops. Click here. Yeah, I agree. Profiles is sort of the idea of like a unique entity, a individual item that's operating within the set. So that might be profiles. So then if profiles are our vertices, anybody want to share with me, what did you make your edges in this case? What do the edges represent? Yeah, sure, finish it off for us. Relationships, sure. And in this case, what kind of relationships do we have? Yes, okay. I like the way that you said that. So if you read the prompt, if I ask you what kind of relationships are involved in this ecosystem, you could say friends and you could say followers, right? There's sort of two distinctions there. And if you can't tell, I lifted this from a lot of different social media platforms. Facebook has the idea of the distinction between friends and followers. I think LinkedIn even has the distinction between connections and followers. And in that specific situation, the idea is that a follower is somebody that can connect to you, but you do not necessarily connect back to them. Whereas a friend is, and I can't remember the exact language you said, like bi-directional sort of connection. But a friend is somebody that you connect to and connects back to you as well. So follows and friendships would be sort of what we're representing with our edges. And I think that that then leads us to these further questions about what information do we need to store in each of these edges? I will probably in all these design questions also ask you what information do you need to store in each of the vertices. You know, remember each of these things, you can think of them as an object. You can think of the vertices as an object. You can think of the edges as an object, and they need to store information. So specifically talking about these edges, let's take a look. Actually, let's see. Can I even show? Hang on. I'm trying to figure out how I can easily do this with all the devices I have available to me. That seems somewhat promising. Okay, I'm going to present this for a second. Okay. Can we see this? Here's the votes. Oh, I know. We are living in a weird future right now. Okay, so here's the votes. So 84 of you elected to make your edges directed. 6 of you elected to make them undirected. Yes? You're right. Hang on. Yay, there we go. Thank you. Now you see what I see. So here's how they sort of shook out. And you can see there I added that like, both, because I intentionally chose this like friendships are sort of bi-directional. And when we have bi-directionality, that sometimes is represented in an undirected graph, because an undirected graph, by definition, all of the edges are bi-directional. But as soon as we put those little arrows on it, then the edges only have one direction. So I'm going to say in this particular context, I totally understand why you're like, both? I personally would select directed. And then what I would do with that, and now I'm going to go back to the desktop, and I'm going to click, is then you just need to add 2 edges for every friendship, but only 1 edge for every following. Yeah? And so that way we have directed edges. It will enable this idea of the followers meaning like a sort of unrequited relationship, a one-directional relationship. And then the way that we represent those bi-directional relationships is we just need 2 edges back and forth. Yes? Great question. So can there be different types of edges because we can store information in them? And I think that sort of leads to our last question here, weighted or unweighted. So you can store information in the edges. I could imagine you having, say different types of edges, and you can, for example, create graphs that have like different overlays, right? So like maybe you have a graph where a bunch of the edges are, say, like the physical roads, and they have a bunch of different fields in them that represent the traffic density at different time periods. Or maybe you have different edges that represent this is a bike path versus this is a road versus this is a walking path. And maybe you indicate those things in fields. You could do it that way. If possible, you probably want to rely on trying to represent things without adding fields whenever possible, because that will open up options for you in terms of graph algorithms. And we're specifically going to spend all of today talking about how we actually write code that traverses these magical things called graphs, what those algorithms mean, and how we can start to adapt those algorithms to get questions answered about the state that we are representing. When I'm specifically asking weighted or unweighted, I am asking about one of those pieces of information. I'm typically asking about a numerical value, and that weight can represent whatever it sort of needs to represent in your scenario. Similar to how like min heap and max heap, that number represents priority, and it's up to you how that priority sort of maps to a number. Weights are a similar thing, but when I say weight, I just mean a number associated with each edge. So in this case, would we go weighted edges or unweighted edges? Do we need a number associated with each of these relationships? No, I think I agree with you, and I think I did unweighted, for example. So like we can kind of get all the information I need from the edges just by them being directional. Yes, question?
So we can have an example, like I know Instagram has like close friends.
Mm-hmm.
So that would be an instance where we have weighted.
Ooh, I like this. So we could say like Instagram has like close friends, right? And so in Instagram, friendships aren't inherently bidirectional though, right? Like if somebody follows you on Instagram, you got to go back and follow them, right? Isn't that the case? I should know that. That's like the one social media platform I use. Yeah, like you can follow somebody, that doesn't mean they're going to follow. So we definitely would want directed edges in that case. But I think you're absolutely right in that we probably want some type of indication of close friends, and that's probably not going to be easy to do with just directionality. I probably would put that as a field, for example. So, we could make that as a field like true close friends or false not close friends. That wouldn't be what I would necessarily call a weight. We could, however, for example, start to do sort of like meta graphs where maybe we calculate like the number of incoming followers, the number of incoming close friends, and maybe that number becomes a weight. But I think like close friends versus regular friends, we probably have some field that indicates that that connection is a different type, similar to our, like maybe this is a bike path as opposed to a physical road kind of thing. Yeah. Yes?
Would something like the length of how long you've been following, would that be something that would be like appropriate for weighted or unweighted?
That could be very interesting. Yeah, like let's say like the thing that immediately comes to my mind in that situation, and I'm sorry if this is traumatic, but like the length of a credit card, like the longer you have a line of credit, the like stronger your relationship with that bank is, kind of thing. And so I could definitely see if you had maybe like an ecosystem of you and all your creditors, maybe that sort of weight of time of relationship is something. And so if we were doing some type of algorithm where maybe we wanted to show how somebody's like following grew over time, maybe we put the weight as like the date or something like that, and we can start to do some sort of like amortized analysis of like, hey, when did those incoming connections really spike, or can we map those over time? A lot of times we think of weight more as sort of like, the value or the cost that it takes to travel through that relationship. So like, for example, if it's a physical road, maybe it's a physical distance, maybe it's the time that it might take you to travel pending on traffic. Maybe it is some idea of like how many proteins influence that particular thing, stuff like that. So a lot of times I think of weight as sort of like the toll on that edge, however much it might cost you to travel it, because a lot of our algorithms are going to ask us about, like, let's say, for example, the shortest path to get from one side to the other. And shortest path could be like physical distance, but it could also be the least amount of steps. It could also be the least amount of incline. It could be, you know, all that sort of stuff. The least amount of traffic, et cetera, et cetera. Great questions. Any other questions about this sort of idea of how we start to map real world scenario to graphs? Like I said, we will do plenty more of these, so thanks for going on that journey. I should have filled out this slide, but I didn't. All right, Administrivia, we're going to fill it out together as we talk. So midterm design due tonight by 11:59 p.m., no late submissions. So reminder that that's happening. Also, P3, if it hasn't already been, will be released. It's all about heaps, and specifically implementing heaps with that array that we talked about. Remember, there is a lecture where I specifically show you the array and then the equations. That slide's probably going to be a good friend of yours during that assignment. Keep in mind that P3, this will be a 1-week assignment. And office hours starts back up today. So I will be having my office hours a little later this evening if you would like to join me on Zoom. Also, just as an FYI, you know, like exercise 4 will go out this Friday. And it will be all about graphs. Any administrative questions or any questions about the simulated exam that is currently out? Okay. Wow. All right. Very suspenseful, Google Slides. Let's maybe give you another try. Oh, okay. There we go. All right. All right. There we go. Okay. So Monday, we did our introduction to graphs. Here is a bunch of that language that we used. So we talked about weighted. We talked about directionality. Degree is a term we're going to use a lot today. Degree refers to how many edges are connected to a given vertex. If it is an undirected graph, we would just say degree. But if it is a directed graph, we might say in degree, meaning how many things are connecting into me, and out degree, how many things do I connect outwards to. A cycle is our ability to start at one node, travel through edges, and return back to that original node. And a path is the number, like the order of vertices in which we might traverse across a graph. So a path could be, say, like A to B, and then we can't go anywhere else. Or it could be, say, C to D to B. Those are all examples of paths. And then a self loop is a edge that turns around and points back at myself, meaning its origin and destination are the same. And then parallel edges are edges that have the same origin and the same destination, but they're different vertices. And you might be like, why would you ever have a parallel edge? But we just talked about a bunch of different types of connections. So that might, for example, maybe we have a connection that's regular following and also close friends or something like that on Instagram. This is just reminders. Reminders here about how you actually implement a graph. There are 2 generally accepted ways to do it. Very rarely will people actually create objects with references between them. Instead, we typically have something like an adjacency matrix where we sort of have a 2-dimensional array where, like, say, the columns represent the destination and the rows represent the origin. So this one here means that there is a connection from A to B, which is like this here. And then keep in mind that if it is bidirectional, in the adjacency matrix situation, we gotta put 2 entries in there for every 1 edge. So the adjacency matrix is sort of by design a directionality implementation, but you can still represent a bidirectional graph in it. You just need to put 2 entries. The adjacency matrix is super good if you're not going to change the number of vertices a bunch. You're just going to change your edges a ton. Or if you have a very dense graph, meaning you have a lot more edges than you have vertices, because it's constant time to sort of like find an edge, add an edge, remove an edge. It's really optimized for like edge manipulation. But adjacency list, that is the way that you're going to probably be implementing your graphs. It's a little bit more of the popular implementation because it's much more of a vertex forward type of implementation, which most graphs are. And we're going to, in this class in particular, be assuming that you're going to implement it where you've got a, there we go, a hash map sort of thing with destination, a collection of destinations as the keys. So here, for example, we have like A as the origin. A can connect to B and C, and then maybe this is, for example, their weights. So if I wanted to get, the weight of the connection between A and C, if there was a number here, I would get A, I would find C in this collection, and then I would find that. So again, see how we sort of have these collections of collections here, which is another reason that graphs are very popular interview questions, because people love to ask collections of collections interview questions. Yes. Mm-hmm. Ah, great question. And you're right. Look, there's not even a little E down here. What should really be here is there should be an E like down here. It just doesn't have anybody connected to it. So there should be an E somewhere on here. E is still considered part of this graph. And for example, we would probably want to include it in our set of possible origins, because maybe at some point we're going to build a road along there, or we're going to connect the electricity or the water pipes or whatever we're going to do in order to bring that vertex into connectivity with the graph. But a reminder that not every vertex has to be connected for it to be considered part of the graph. A lot of times we refer to the disconnected subsections of graphs as the components. So a graph doesn't have to be one singularly connected component. It could be multiple, like little sub-connected components. And we'll talk a little bit about that in more detail when we get to some of the fancier algorithms later on in the course. Any other questions? Yeah. So the 1, and this would also make this slide more clear, that 1 right now is representing the weight of these edges, but the edges don't have any weights on them. And you might be like, then why do we even need to care about this? Because actually you'll find that a lot of the algorithms require weights as a way to run the algorithm. And if you have an unweighted graph, the way to still use that algorithm on an unweighted graph is you just set all the weights to 1. It kind of ends up being the same type of thing. So that's what's happening here, is that this graph representation is storing the weights as 1. Yeah, question in the middle.
I have one question. So this is the hash map, right? So for hash map, you can only have 1 chain, right? But in this case, like you have a multiple chain in each bucket. Is that possible?
So what's happening here is that we've got like a bucket. And that bucket stores A as the key, and then the collection of vertices that A connects to as the value. This collection is also a map, where this collection is a collection of key value sets, where B to 1 is 1 key value set, C to 1 is a key value set. So it's actually like a map of maps. Yes. Good questions. So let's start talking about how we actually use these things and write some code to understand what's going on in the graphs. You can read the trade-offs. Here's the runtimes. So let's talk about how we actually traverse these things. Sort of the first thing we're going to want to do with our graphs. So let's say we have a graph that looks like this. And our problem is we want to see if a path exists from S, source, to T, terminal. So I just want to see if somewhere in this graph I can get from one node to the other. Very, very common question to ask about graphs. You can imagine this could be a situation of like putting in, you know, destination A and B in Google Maps, or trying to figure out, hey, if I post something on my Facebook, is my mom going to see it because of our mutual friends? The answer is no, because my mom is terrible at Facebook, thank goodness. So we just want to try and figure out an algorithm. How can we tell if S and T are somehow connected, even if they are not directly connected? That's the problem we're trying to figure out. So we can use recursion where, okay, maybe S is not directly connected to T, but we would consider S to be connected to T if S's neighbor is connected to S's neighbor is connected to S's neighbor is connected eventually to T. And that is inherently a kind of recursive problem, right? So here's some recursive code. We could say take in vertex S and vertex T as parameters. And we can just say, hey, like if we're looking at the same thing, return true, we've made it. Otherwise, for each one of my neighbors, loop over each neighbor and tell me if that neighbor is then connected to what I'm looking for. If that neighbor is, cool, return true. Otherwise, return false. Eventually, hopefully I'll find myself a true. Does this work? Does anybody see any problems with this right off the bat? Yeah. The runtime. Oh, good idea. The runtime. Anytime I say, here's a recursive solution, hopefully your spidey senses should be going off and saying, gosh darn it, unless it's one of those real fancy cut the input in half kind of recursive solutions, which have that logarithmic runtime, it's probably a tree kind of looking recursion, which can have that 2 to the n type of runtime, which is not good. So yeah, runtime, no bueno in this one. Yeah. Yes, infinite loops. Good eye. So what would happen here is we would first start off if 0 is our source, and we'd say, hey, is 0 7? It's not. So recurse on 1, and then we would loop over all of 1's neighbors, which happen to include 0. And so I would end up in this loop back and forth between like standing on the node with 0, standing on the node with 1. And this makes sense because like we don't have that same sort of like linked list structure where I know where I started, I know where I'm going, or same thing with trees, you kind of start at the top and you work your way down. In graphs, there is no sort of directionality like that, so it's very easy to end up in these infinite loops. And so that is exactly a problem. And the way that we are going to solve this problem is we're literally just going to remember where we've already been. And if we've been there, don't go there again. So here's our same code, and we've added a set that's highlighted up here. And we are going to essentially, quote, mark each node as sort of like processed or seen or visited or stepped on or whatever, you know, makes most sense in your brain. And then every time we recurse, we're going to check like, hey, it's not something I've already checked, right? So in the beginning, we started with 0, and then we said, hey, is 0 equal to 7? No. So add all of 0's neighbors, which is 1. And then I'm going to ask myself, is 1 7? No, it's not. Now I'm going to loop over all of 1's neighbors, which are 0, 2, and 4. But because of this nice new if statement here, I'm not going to go back to 0 accidentally. So then I'm going to add 2 and 4. I'll sort of recurse down to 2. I'll add 5, you know, and so on and so forth. And that'll let me sort of crawl neighbor by neighbor across the graph. And so this way, I am only traversing the graph based on neighbors, meaning I am only traversing the graph based on existing edges. So if I have a disconnected node or a disconnected component, I wouldn't reach it, which is exactly what I want for this problem. I'm trying to measure connectivity. So if it helps to think of this as sort of like the crawler, I'm adding in neighbors as I encounter them. I'm respecting that I can only travel to neighbors as I sort of find them. Yeah.
Is there a reason why we're not passing this as a parameter and using it as a global parameter?
In this particular case, as you can see, that little assume global, that's mostly because I didn't want to add in another parameter here. You'll make and destroy these sets of visiteds over and over again, so on and so forth. So there's not any rhyme or reason. Honestly, that's more just me trying to keep the lines narrow for the slide purposes. Yes. And so specifically this idea that I start on a node, I add all of the neighbors to that node to some type of collection of like, hey, go check those out. And then I have a separate collection that says whether or not I've already checked them out. That is the basis for every graph algorithm. And from here on out, we're just going to add on to that foundation different things that we can do with this idea of some type of collection that tells us where we've yet to go, some type of collection that tells us where we've been. Yeah. Ooh, to pick the shortest path, do we have to do like a recursive backtracking where we find all of them and pick the shortest? Actually, a gentleman named Dijkstra, who was born semi-recently, invented an algorithm. And we're going to spend all of Friday talking about that exact thing. And the answer is no. There's a little bit better solution than that. So this code works. This is a recursive solution to what we are going to call depth first search, often abbreviated as DFS. This is the classic graph traversal. If your brain is really into those pre, in, and post order traversals from trees, this is kind of similar analogously to one of those where it's about how you move through and how you process things as you move through the graph. So in depth first search, the way this kind of works is we start at a node, we look at its neighbors, we pick its first neighbor, and then we look at all of that neighbor's neighbors, and then all of that neighbor's neighbors, and then all of that neighbor's neighbors. So we sort of do this depth sort of like plunge down one particular directionality. If this was a tree, you'll find that this kind of looks like a singular path from the top to the bottom. And so that's how I remember depth first search, is I kind of imagine a tree, and I realize that it's going to go down many levels of the tree before it kind of comes back up and does anything. But here's an animation so you can see here's a depth first search where I start at source. I then look at my first neighbor 2, and then I look at 2's neighbor 5 before I ever come back and look at the other neighbor of 1, 4. And then I now look at 5's neighbor, which is 6, meaning I haven't processed 8, right? Like I picked one of those and then I picked 9. And now I start to kind of like roll back up, and I can be like, okay, well now process those ones, 7, 8, 4, and 3 that were neighbors that I didn't finish off in that depth play. But like we mentioned, this is a recursive solution, and graphs can get really, really large. So a recursive solution to a graph is going to actually end up being pretty unwieldy for us. And also, I'm not going to ask you to write recursive code when writing your graphs. So, oh yeah, here's this aside for tree traversals. This is what it literally looks like. Oh, thanks, past Casey. Yeah, there's depth first search. You can imagine it kind of explores all the way down to a branch, and then it does things. Yep, there we go. Wow, look, past Casey had the same thoughts as current Casey. Thank you. Okay, so that is one type of traversal. Here is another type of traversal. This is just about another ordering of how we visit things. This is what we're going to call breadth first search, or BFS. And in this situation, instead of just pulling on that sweater thread of like my neighbor's 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 neighbor, I'm instead going to kind of process things in what I think of as sort of like rings, or like, sort of like splash zones, if you will. We're kind of going to go zone to zone, meaning we're going to look at all of the neighbors for a particular node, and then we're going to look at all of the neighbors for its first neighbor. So we look at all of like my sort of like next door neighbors before I really let myself get too much further. So if I say start at source again, I would look at 2 and 4. And then I would look at 5 because that was the neighbor of 2. And 3, which was the neighbor of 4. And then I would look at 6 and 8 because those are the neighbors of 5. And then I would look at 9 and 7 because those are the neighbors of 6. And so you can see, if you compare this to DFS, I kind of like, it's almost like a wave that kind of pushes eastward across the graph there, as opposed to that singular depth play. The runtime of these two things, when I show you the code for it, will be equivalent. So BFS and DFS, if you're just trying to measure connectivity, are equivalent. But you might need to know this order in which you visited nodes to adapt your algorithm for later. You know, like maybe you want to see like how many levels out can I go before I hit something, and I want to measure level by level. Or maybe you want to see how deep does my relationship tree go, so I do depth first. So that order does matter in terms of the specific question you're trying to ask, but just for connectivity, both of these are equivalent. So layer by layer, here is actually a sort of an overlay of the role or the order in which we visited these things. You can think of this as like sort of zones. So how do we translate this into code? And notice here that like we are sort of interrupting recursive calls. We're looping over our immediate children, but we're not like allowing the recursion to just get down to the base case. So instead, we're not going to end up doing a recursive solution. We're going to end up doing a iterative solution. And here is sort of like the next big structure that we're going to add to our algorithm is we are going to add in a queue. So now we have our two structures. Previously, we just needed to make sure that we hadn't already processed something. Then we could just recurse down. Now we are going to actually sort of store up who do we need to look at next. And then we're going to loop over the queue to dictate which nodes we're going to process and in what order. So I'm going to call the queue perimeter. You can think of that as like next door neighbors kind of thing, but that's the order in which I'm going to visit the neighbors. And the set is the exact same set as before, just have we already sort of, quote, visited or processed this node. So we kick off the algorithm by adding the source to the set of visited nodes, because like I'm starting here, I've quote visited it, and then I'm going to add it to the set of nodes to sort of like start looking at the perimeters for. And then I'm going to loop. And so you can see right away, I'm going to remove the first node from the queue, which is just source start right now. And then I'm going to loop over every edge coming from that vertex. And I'm going to look at every one of my neighbors. So this vertex in here, this vertex 2, that's each of my neighbors. So in this context, it started with 1. I'm going to loop over 2 and 4. For each of my neighbors, if I have not already visited them, then I'm going to add them to the list of things to be visited, like to process, and I'm going to mark them as like, hey, I've sort of been there. So the way that this code then works is I start at 1. 1 gets added to the queue. You can see, right? So that 1 got added to the queue right here on this line. Now I'm going to loop and I'm going to add 2 and 4 to that queue. And that comes from this loop right here, because neither of them had been visited yet. So we were going to add them previously or add them into the queue. So now I've got 2 and 4 sitting in the queue. Now when I come back around, I'm going to remove that 2. That's my new from. I sort of like looped back around. And then I go and I loop over 2's neighbors. And 2 only has 2 neighbors, 1 and 5. But the 1's already in my visited set. So I don't add 1 back into the queue, but 5 wasn't in my visited set. So it got added to the queue coming after the 4. And then I loop back around, I remove the 4, and I see 4's got 3 neighbors. It's got 1, 5, and 3, but 1 and 5 are already in the visited set. So I only add that 3 into the queue yet to be processed. And then I keep going, and so on and so forth, like that, until I visit everybody. Questions on how this BFS code works? Because this is the foundation. Like, get very comfortable with this code. This is the kind of code that you could use in your interviews, and you just adapt it. Like, maybe you want to check if there's connectivity. Maybe you just want to count the weight. Maybe you just want to see, you know, like, can my mom see my stuff if she's a friend of a friend, right? Like that's what I'm trying to solve with this one. Yeah. What is edges from this one. So what this is doing here is you can see this is removing from perimeter. So that's like when we've come back around and we're pulling something off of the front of this queue, and it's time to then loop over its edges. So originally it was 1, and then we pulled 1 out and we queued up 2 and 4. And we got that 2 and 4 by pulling the 1 out, and it was the 1 was the from, and then this loop was over 2 and 4. And then when we looped back around to the while loop, the 2 became from, and then we looped over 2's neighbors, which was 1 already visited, and 5, and we added 5 in. So we're kind of doing this thing where, like, originally something gets added into the queue when it's considered a 2, like when I'm like standing on a node looking out towards my neighbors, and then eventually when the while loop comes back around, when I pull you out of the queue, I'm like standing on you, and now you're the origin. So you get added into the queue when you're like a destination, I can see you over there, and then you get pulled out of the queue and you become the from vertex when you're now the destination and I'm looking for your neighbors. I don't know if that clarified things. Other questions? Just the sort of swapping. Start on a node, look at all of that from nodes, 2 neighbors, loop back around, pull out something that was added as a 2. Now it's the from, look at all of its neighbors, add them as 2s, so on and so forth. Cool, great, animations, helpful. And this is really helpful. The queue will let us specifically sort of like navigate this in this BFS way. It makes sure that we're processing things in the order in which we see them, meaning it like doesn't sort of do that depth thing, right? Like it doesn't interrupt any of the processes. I'm sort of processing nodes and all of their neighbors all in a specific order. So what if we could adapt this to do the same type of depth first search, but instead of doing it recursively, which we know doesn't have great runtime, can I do it in a more optimal way? Oh, what if we changed that queue to a stack? Now I'm changing the order in which I'm going to process any given node's neighbors. And in the queue version, the BFS version, I'm going to look at all of my neighbors. And then after I'm finished with all my neighbors, I'm going to go to my first neighbors, all of their neighbors. But in a stack, remember, we're sort of going to keep pushing things down. And so the stack gives us that sort of inherent interruption type of behavior where what I'm going to do is I'm going to start at source. I'm going to look at all my neighbors. I'm going to add all of my neighbors to the stack. And then I am going to look at my first neighbor and push its neighbors on. And it's going to push any of those extra neighbors further down. And so the stack ordering is going to give me that, like, I'm not waiting to do these sort of rings. Instead, I'm just like, find my neighbors, first neighbors, first neighbors, first neighbor. One thing about this that can be a little funny is that, so you can see up here in the highlighted, technically all I've done is really that I've just changed the queue to be a stack. It's just changing the order in which I'm processing the neighbors. But there is one other change. So we did that change. The other change is that we can't immediately mark a node as visited like we were doing in the BFS situation. Instead, the stack really becomes like a set of nodes to look at some other moment in time, and according to, you know, like how the stack ordering property is. So we do need to make sure that we are, instead of marking, like adding it to the things to look at and also marking it as visited, we just add it to the list of things to look at. And then once we're all done with pushing everything, you know, into the collection here, then we mark where we're currently at as visited. Yes.
How would we know when we use DFS or DFS if there's like a optimal situation for each?
So the question is, when do we use BFS versus DFS? If you are just measuring connectivity, they are equivalent. So dealer's choice. If it is a situation where, like I said, maybe you are trying to measure how many like rings of connection out, And then you don't need to like keep going after that. Maybe you want a BFS because maybe you don't need to go all the way from source to target. Maybe, for example, you only need to notify somebody of their COVID exposure every like 3 levels of connections deep kind of thing. So maybe you want to notify everybody you were physically present with, everyone they were physically present with, and everyone else they were physically present with. That would maybe be more of a BFS kind of question, right? A depth first search, that might be a question where I'm very curious about like, what's the like furthest distance that I can get from one to the other, or, you know, and so maybe I don't care so much about having multiple neighbors as long as there exists like one directionality. And so it totally depends on like the scenario and what questions you're asking yourself as you go. DFS, for example, like if you're just trying to get to like, can I get, you know, one connectivity, you know, it could say, for example, like, and you know, things are far away. DFS is going to go deeper into the graph faster than it's going to go wide. And so if you know your like nodes on the other side, you might get there faster with DFS than with BFS, but that's not actually a guarantee. Also, there is no mathematical guarantee for that. So asymptotically, they perform the same. Any questions about this BFS DFS code? So like I said, BFS then becomes the foundation of pretty much everything, and now it's become the foundation of DFS back again, yeah? So we talked about DFS and BFS iteratives. Be careful using the recursive one because we talked about that runtime. So here is that code. Okay, great. Okay, I have 5 more minutes. I want to show you an example of an algorithm that is built off of BFS. This is actually a pretty useful little algorithm, and it always gets squeezed in this course, and I'm really sorry, topological sort. I keep moving you around. Topological sort is a way to sort a graph in a particular order. It does require that you have a directed graph. So if you have an undirected graph, you might have to transform it into a directed graph. And so a lot of times what we're trying to do is we're trying to order things so that any destination node is ordered after an origin node. You can think of these as sort of like dependencies, or maybe on the reverse side of things, prerequisites. So for example, like we have this sort of like ABC graph up here. A points to B and C, which means A must come before either A, B, or C. And then we see that B must come after A and must come before C, but C can't come through any of those. And so we'll end up with a topological sort of ABC. That's kind of what our goals are here. The actual implementations for this is actually how computers determine which code files to compile and when. Because you've got to kind of compile code that is imported or included before you get to your code so that your code can understand it and you don't get that cannot find symbol error. This is literally how it does that. Or maybe more helpful in our brains, maybe it's a bunch of class prerequisites. So maybe you have like CSE 143 and its prerequisites are CSE 142 and Math 126. It doesn't matter if you take 126 or 120 or 142 first, as long as both of them come before 143. And you got to take 143 before you take 373 or 374, and you got to take 373 before you take 417. And I just need some type of ordering of how to like put together my classes. The way that this algorithm works is I think of things as having a number of in degrees. Any node with a 0 in degree is somewhere I can start. You can think of that node as having no prerequisites. So I can take any class that has no prerequisites just right away, right? Then, once I process something with 0 in degrees, I kind of think of myself as deleting it from the graph. And then that like reduces the number of in degrees to anything it pointed to. And then I ask myself again, now is there any more nodes that have 0 in degrees? Sweet. And then I delete all of its connections, and then I just process things as they have 0 degrees. So that's one way. There's also, if you can't tell, there is not necessarily always a deterministic topological sort. Sometimes there can be multiple correct answers. You know, like I said, it doesn't matter if you take Math 124 or CSE 142 first, as long as they both come before 143 kind of thing. So here is a topological sort of that class prerequisites. And this is then the code for our topological sort. And you can see looks a lot like our BFS code. Here's the differences. I've got my queue, I've got my set, but now I have this kind of map where I'm counting in degrees, and then I'm adding whichever nodes have 0 in degrees to my queue first. And then as I loop over my queue, I am going to update the in degrees by removing them, and then anytime I hit another 0, I'm going to add it to the things to process again. But this, even though I sort of split it up into 2 boxes, is essentially the exact same code as BFS. The only thing is I added this for loop to calculate the in degrees, and I added these sort of if statements here to determine who gets added to the queue when, based on as I'm updating in degrees. Questions? Cool. Okay. I will leave it there. Please go to section tomorrow. You're going to do a lot more traversal conversations. The TAs are going to help with the language. And then come on Friday so we can talk about that shortest path problem, which inherently ends up being one of the most useful algorithms in all of computer science. Thanks so much, everyone.